Today, I want to talk about what I believe is the most exciting time in computing over the past decades, because we're at the beginning of a revolution that will be at least as transformative as the invention of the internet. In this AI revolution, computing infrastructure has played and will continue to play a central role. But what makes this moment truly exciting is that reinventing computing infrastructure is no longer just nice to have, it is a necessity. To achieve the highest level of efficiency, we must rethink our computing infrastructure design holistically across the stack, spanning machine learning, computer systems, databases, and computer architecture. Before diving into this argument, let me first bring you back to 2012, a monumental year in the history of AI, when the famous AlexNet was invented. If you look at the computer system used to train it, it was surprisingly modest, just a pair of commercial GPUs designed for gaming. 10 years later, the system used to train the OpenAI's GPT-4 model contains 25,000 of GPUs, with each GPU being already 1,000 times more powerful than the one used to train AlexNet. So just within 10 years, we ended up with a computing infrastructure that is 10 million times more powerful than before. The story isn't just about NVIDIA. All the major hyperscalers, Google, Meta, Amazon, and Microsoft, they're all actively investing on their own AI hardware and software infrastructure. For instance, Microsoft committed $80 billion just in this single year for their AI infrastructure investment. And if you look at the server industry, we find that 70% of the total value in 2025 actually goes to AI servers. And this is a significant shift for computing because it means more is being invested into those AI servers than in traditional CPU-based servers, which have been the foundation for computer science research for decades. With such massive investments, the efficiency of these ML systems matter more than ever. Machine learning system efficiency is exactly what I'm going to talk about today. But rather than talking about the remarkable progress we have made in model inference and training infrastructure, I would like to argue the future really lies beyond this. Specifically, I'll show you why vector data systems are becoming increasingly critical in machine learning infrastructure, which is a highly valuable yet underexplored topic today. To illustrate this, let me first introduce retrieval-augmented generation, or RAG in short, which is an emerging large language model serving paradigm. The key idea of retrieval-augmented generation, or RAG, is about pairing large language models with retrievals from external knowledge databases. In this example, the user asks a question about Thomas Edison's inventions. Now, instead of letting the model to generate the answer directly, this question is firstly used to retrieve knowledge from a database. So essentially, it's very similar to invoke a search engine call like Google or Bing, where we ask a question and get some related web pages. And more specifically, this retrieval is conducted through vector search on a vector database. Here, each document in the database is processed by a neural network and encoded into a vector, which represents the semantic of the document. Now, when a question arrives, it will be also turned into a query vector and compared against the database vectors. The database will then return the most relevant database documents based on vector similarity. In this example, in response to this query about Thomas Edison, the retrieval procedure might find documents highlighting his contributions to phonograph, to cameras, etc. And then the retrieved documents are included into the prompt, so the model can now generate a more well-informed response. By including the vector data system for retrieval in the pipeline, RAG has several key advantages over regular LLMs. First, the model is less likely to hallucinate given the retrieved knowledge. And second, the model can be coupled with a private database to provide more personalized answers. Third, whenever there is new data or new knowledge, instead of retraining the model over and over again, we can simply update the database, which is much cheaper and also much faster. And finally, RAG may also reduce the generation cost because it can significantly reduce model sizes, an argument I will explain later on in this talk. And due to these many advantages, it's not surprising that RAG has gained attention not only in academia but also in industry, where all these companies are racing to integrate RAG into their production systems. And as RAG is becoming the new standard for reliable large language model serving, it is essential to serve these workloads efficiently. And if you think about what is interesting about RAG, there are several key aspects. First, vector databases and retrievals are playing an important role in the RAG pipelines. So it's no longer just about model serving. And second, there are a wide range of RAG algorithms out there beyond the demo example I show here. Some propose adding additional models to the serving pipeline, while others suggest fancy retrieval patterns. As we'll see later on in this talk, the workload characteristics across all these algorithm variants really look completely different. And finally, depending on the algorithm configuration, RAG may consist of multiple system components, including models and retrievals, and these components can be served by heterogeneous hardware. For example, ML accelerators for different models, and then CPUs or even specialized hardware for retrievals. So even if RAG seems to be a simple concept, there are really multiple aspects that we need to pay attention to. Databases, algorithms, systems, and hardware, and they're not independent to each other. This is a unique challenge about machine learning systems nowadays because a lot of interesting research actually happen across the computing stack. So we can no longer just focusing on a single subproblem and treating other components just like black boxes. This is exactly my research style. I work on full stack machine learning system research rather than focusing on a single subproblem. And these efforts includes improving algorithms, optimizing retrieval and data systems, designing better system architectures, and even building customized hardware. Now let me give you a brief overview of my research during my PhD. My most recent research tackles efficient rack serving, and I've done several pioneering work around it across the computing stack. From the system level, I proposed RAGO, which is the first systematic performance optimization for RAG. RAGO shows the drastically different performance characteristics across different RAG algorithms and optimizes RAG serving performance systematically. From the hardware level, I proposed Chameleon, which is the first heterogeneous accelerator system for RAG. And the key idea here is that if in the future every model is going to be connected to the internet, then the retrieval performance is going to be crucial. So we should include not only LLM accelerators, but also design and include retrieval accelerators in RAG serving systems. Moving up the stack, I also propose pipe RAG, which is an efficient algorithm for iterative RAG, where we speed up RAG serving by overlapping the latency between retrieval and generation by approximate data prefetching. Before RAG, I also worked on vector search, a critical component not only in RAG systems, but also in commander systems, search engines, etc. And specifically, I work on how to co-design the retrieval algorithms and the underlying hardware. This work includes Fence and Falcon. They target two most popular vector search paradigms, quantization-based search and also graph-based algorithms. Before RAG and vector search, I also work on data systems on modern hardware in general. For example, I work on recommender system, a topic that is also related to vector data because one of the key components in recommender systems is the many embedding vector tables. And this research set the foundation for my later work related to vector search and then RAG. Today, I'll mainly talk about two of my most recent work, RAGO and Chameleon. They're pioneer work that addresses RAG serving performance at the system level and at the hardware level, respectively. Let me first introduce RAGO, the first systematic performance optimization for RAG serving. You might wonder, shouldn't it be straightforward to combine LLMs with retrievals? Well, it turns out RAG is actually far more complex than it appears. Since the invention of RAG, there have been numerous RAG algorithm variants. Some propose adding additional models to the serving pipeline, while others propose various retrieval paradigms. And these RAG algorithms are evolving so rapidly, so not a single algorithm can outperform all the other ones across all the dimensions. And because of these different algorithm configurations, the performance characteristics across RAG algorithms also differ a lot, and they look like completely different subproblems. And to show you this point, let's look at a couple of concrete examples. The first example in RAG is using these large language models with hyperscale retrievals from the internet. So essentially, it's very similar to connect the models to Google or Bing. And recent research has shown that RAG systems, even with a 10 times smaller model, can match or even surpass the quality of larger models without retrievals. So the argument here is that smaller model plus hyperscale retrieval can be used as an alternative for larger models. And this is because LLMs relies on their vast number of parameters to remember the knowledge in the training corpus. For RAG, the model can actually retrieve knowledge from the large corpus, so it doesn't need that many of model parameters to remember everything. And the workload here is a pretty simple three-stage pipeline. So first we run the retrieval. Here the retrieval setup is taken from a paper by Google DeepMind, which is an internet-scale corpus containing more than 2 trillion of tokens, and that means 100 terabytes of raw database vectors. And then we have the two inference stages of the LM. The first stage is the prefix stage for prompt computation. So we take the user question as well as the retrieved documents as input, and then we generate the first output token. And the second stage here is the decoding phase, where the subsequent output tokens are generated one at a time. Now let's take a look at how RAG with smaller model actually perform versus a larger LM. So in this plot, the x-axis shows the time to first token latency, meaning how long the user will wait before they see the first output token. And the y-axis shows the throughput per chip, representing the request the system can process per second, normalized by the number of accelerators. And here, we're comparing RAG with a smaller AB model versus a larger 70B model without retrieval, assuming they can achieve similar generation quality as evidenced by previous studies. And here, you can see that RAG indeed outperforms the larger LLMs in terms of QPS per chip by a factor of 1.5x. But this advantage is actually far from the 10 times of model size differences. So why is that? Well, there are two reasons. The first reason is that RAG requires a longer prompts to incorporate these retrieved documents. So instead of saving 10 times of floating point operations according to model size differences, the actual saving is only around 3 times. And the second reason is that the retrieval overhead at such a large scale is very high. It can be even more expensive than the model inference process itself. So now let's take a closer look at this retrieval overhead. Here, the x-axis in this plot shows the different number of queries at the beginning of the generation process. There can be multiple queries for retrievals because the user's question can be complex or vague, so we may need to break it down into multiple sub-questions in order to achieve better retrieval quality. And the y-axis here shows the time distribution across the retrieval and inference phases. And for this AB model, even with only one query vector at the beginning of the sequence, it already becomes the main performance bottleneck. And then the time consumption of retrieval is even higher if we have multiple queries. So to fully claim the benefit of reduced model sizes, we really need faster retrievals at large scale. I'll address this bottleneck in the second half of this talk by hardware acceleration. But before that, let's switch to a second use case of RAG. And here, instead of using hyperscale retrievals, we want to use RAG for long context processing. For example, a user may upload a lengthy document in real time and start asking questions about it right away. And here, a straightforward solution is to put the entire document into the prompt, but this solution is often very expensive because a large number of tokens to be processed by this large model. For example, OpenAI charges $60 per million input tokens for their GPT-4 model, but we really don't want to spend that much just to answer a single question. But instead, an efficient alternative is to use RAG. And here, we can construct the database on these documents in real time and retrieve relevant information from it. So we don't need to put the entire document into the prompt. And RAG can achieve hundreds of thousands or thousands of times of performance improvement compared to the naive long context language model, will still achieve similar generation quality. So how does the database construction process work? Well, it's pretty simple. First, the documents are chunked into passages, let's say 100 tokens per passage. And then each passage is encoded to a database vector by a small bird-style encoder model. And one of the reasons why RAG is cheaper than long context language model is that we're using a very small model here to process the input tokens. So even if we construct the database at serving time, it's still much faster than putting everything into the prompt. Now we have the vectors for each passage, and since we're talking about users' documents, the database here are usually millions of times smaller than hyperscale retrieval that we just seen in the first study. So what's the performance characteristics of this case? In this plot, the x-axis shows the different input document lengths ranging from 100K to 10 million tokens, and the y-axis shows the distribution across different RAG components, including encoding, retrieval, and generation. Now specifically, the encoder model here is very small, that is 500 times smaller than the main generative LLM. However, as the contact length increases, the encoding time, which is the blue bar here, still grows and eventually dominates the time consumption. So this means even a small model in RAG pipelines that is 500 times smaller than the main LM can still become the main performance bottleneck due to the sheer volume of tokens that it has to process. Another interesting observation here is that the retrieval time is almost invisible here, even considering we're just using brute force search here without an index at all. So in contrast to the first case study where retrieval performance is crucial, here the retrieval performance is not important at all. For the sake of time, I cannot cover all the 4 RAG case studies in our paper, but even from these 2 examples, we can already see that the performance characteristics across different RAG algorithms can really differ a lot, and they look like completely different sub-problems. So a natural research question here is that how should we design the RAG serving system to accommodate all these workloads efficiently? Well, before solving the problem, we'll first need a clear problem formulation. Essentially, we'll need a unified workload abstraction to represent different RAG algorithm variants. To this end, we propose RAG schema, which is a RAG workload abstraction that mainly describes 2 things. First, which model components do we use in the pipeline? As RAG can contain multiple optional models in addition to the main generative LLM. For example, we may have a database encoder model for long context processing, as we just saw. And then before retrieval, there can be this query writer model to rephrase users' question or breaking down a complex question into multiple sub-questions. And then after retrieval, one can use a resultary ranker model to better evaluate the relevance between the user's questions and the retrieved documents. Then for retrieval, there are several attributes worth mentioning. First is the database size. It can really vary by millions of times, as we have just shown in the long context processing versus internet scale retrieval. And secondly, a RAG can issue not only one query, but multiple queries at the beginning. Alternatively, these multiple questions can also be issued during the generation process, where the LM generates the question and initiates this iterative retrievals actively. With a unified workload representation, we can then start to optimize the system performance for various RAG algorithms. To this end, we propose RAGO, which stands for Retrieval-Augmented Generation Optimizer. Given arbitrary RAG inputs, defined in RAG schema, and also hardware resource budgets, RAGO can navigate the system design space and return the performance Pareto as well as the optimal system configurations. Now let me show you the system design decisions in RAGO with an example. So the first design decision here is where do we place the different models in the RAG pipeline? Do we co-locate them on the same set of accelerators or do we disaggregate them? Both are possible options depending on the workload characteristics of the model and the performance requirement per stage. For example, the re-ranker and the prefix component can be co-located on the same set of accelerators for two reasons. First, they both share the same performance metric of time to first token latency, and second, they are both compute bound. On the other hand, the LLM's prefix and decode phases can be disaggregated over different set of accelerators because first, they optimize different performance metrics with the decoding phase optimized for time per output token latency rather than time to first token. And second, decode phase is more memory bound instead of being more compute bound, so it can be executed on different types of accelerators. The second design decision is about allocating resources. It's about allocating accelerator and CPU resources to different RAG components, given the computational demand and performance requirements of each component. The third decision here is batching policy. Upon receiving a burst of user request, we can either apply the request batch size for all the stages or break the request into micro batches. Both are valid options depending on whether the performance goal is more about throughput or more about latency. So how does RAGO find optimal schedules? In short, RAGO is a cost model-based optimizer, so it's conceptually similar to a query optimizer in database systems. It includes an ML-based ML inference performance model currently supporting TPUs and GPUs, as well as vector search cost models for CPUs. These models are essentially well-tuned roofline models, and based on input workloads such as model sizes, sequence lengths, database sizes, etc., they can estimate the system performance for a given hardware backend with around 80% of accuracy. And then with this component level performance models, RAGO will then assemble the end-to-end RAG serving performance. It will first identify the optimal system configuration for each RAG component that forms the performance Pareto frontier. And then it will combine the optimal configurations for each subsystem to form the end-to-end system design space. And finally, based on the user's performance requirements, let's say optimizing throughput given a certain latency requirement, RAGO will optimize the performance and return the respective system configurations. So to sum up, RAGO bridges the gap between the fast-evolving RAG algorithms and the underlying system support. We show the drastically different performance characteristics across different RAG serving paradigms, abstract various workloads by RAG schema, and also propose RAGO to optimize the system performance for different RAG algorithms. Now let's move on to the second part of this talk. And here I will introduce Chameleon, the first heterogeneous accelerated system for RAG. And as we have seen the first case study of RAGO, retrieval can be a significant bottleneck in RAG systems, especially when coupling small models with hyperscale retrievals. I realized this even before the RAGO project when I worked on vector search and addressed this by hardware acceleration. Before we dive into the solution, let's take a closer look at the retrieval process itself. So in this figure, each point represents a database vector. The dimensionality of these vectors can be very high, for example, hundreds to even thousands of dimensions per vector. And here we're just showing a 2D visualization. Now, given a query vector, the goal of a vector search is to identify the top k nearest neighbors to this query vector. So in essence, it's about finding the documents most relevant to the current context. For very large databases, exact nearest neighbor search can be too costly to afford because it involves a brute force scan over all the database vectors. So in practice, people typically use so-called approximate nearest neighbor search, which trades a little bit of retrieval accuracy for much higher performance. And a widely used algorithm in this domain is known as the IVIPQ algorithm. So the IVIPQ algorithm mainly consists of two components. The first component is the IVF index for search place pruning. The key idea here is to cluster the database vectors based on their data distribution. So at the retrieval time, the query vector is compared against its cluster centroid first to determine which clusters are close to this query vector. And only those clusters of database vectors which are close to the query vector is going to be scanned. So we avoid the brute force scan across the entire database. And the second component here is known as product quantization, or PQ in short. This is essentially a lossy compression technique that can convert high-dimensional database vectors into compact byte PQ codes. For example, a 1,000-dimensional database vector can be compressed into just 100 bytes of this PQ code. I'm going to skip the technical detail here, but essentially, it's about breaking the vectors into subvectors and only store the approximation for each subvector space. So the concept of the IVIPQ algorithm is very simple. We have an index to prune the search space, and then we have product quantization to reduce the memory footprint by more than an order of magnitude. Now let's imagine an ideal large-scale vector search system. So what properties should it have? Well, first we need sufficient memory capacity because for internet scale corpus, we're talking about tens to even hundreds of terabytes of vectors before quantization. And second, we need fast processors to handle the comparisons between query vector and quantized database vectors. And this quantization decoding process will require very intense fetch operations, where each byte of VQ code is fetched first and then used as an address to fetch another value in the distance lookup table. And these intense fetch operations are exactly the reason why CPU are slow at it, because even if both the PQ codes and the lookup tables are already loaded into the L1 cache, the cache accesses are still too intensive and it becomes the main performance bottleneck. So this makes the decoding process being more CPU bound instead of being more main memory bound. Now, what about GPUs? Because GPUs are known for their massive parallelism, and the many cores should compensate for the slow speed per core. So for GPUs, the main problem is the cost because GPUs typically integrate HBM, which is 5 to 10 times more expensive compared to DDR memory, given the same memory capacity. So a cluster with 10 terabytes of memory will require at least 100 GPUs, which costs millions of dollars. Besides, the GPU architecture is not really tailored for vector search. For example, the many compute units on GPUs are barely used during the search, but it still leads to static energy consumption. Today, hardware specialization is not a crazy idea anymore because Moore's law is that, and if we want much more performance, we'll have to do something at the silicon level eventually. Now, given that retrieval can be a major performance bottleneck in ML system, and given that it is a very different workload compared to model serving, we should start to seriously consider hardware specialization for retrieval as well. With this in mind, we started the Chameleon project where I proposed two key system design principles for efficient RAG serving. First, as we just mentioned, to support large-scale and high-performance retrieval, we need specialized vector search accelerators. So we should build a heterogeneous accelerator system including both LLM accelerators and also retrieval accelerators. The second design principle we propose here is to disaggregate these two types of accelerators and letting them to communicate over the network. As we've seen from the RAGO work, different RAG workloads can have vastly different performance bottlenecks. And by disaggregating these two types of accelerators over the network, you can easily adjust the number of accelerators based on algorithm configurations. So we can provide better flexibility as well as scalability. And to materialize this principle, I built Chameleon, a heterogeneous and disaggregated accelerator system for rack serving. And here shows you a high-level diagram of our system design, and let's go over it step by step. First, at the user interface level, questions from the users are sent to the CPU coordinator server. The CPU will forward these prompts to the GPU engine, and here each GPU process essentially consists of two components. The first component is the LLM for generation, just like regular large language model serving systems. But the second component here is actually the IVF index for pruning the search space. The index is here is because although the entire vector database is large, the index is typically very small, and the index scan process can benefit from the high memory bandwidth of the GPU. So the GPU can scan the index and decides which clusters of database vectors should be scanned further. So this information is then returned to the CPU server, and the CPU server will in turn broadcast this information, which clusters to scan, to all this retrieval accelerator. And here, each retrieval node is essentially an accelerated, disaggregated memory node. It includes abundant of DDR memory that contains a partition of the database vectors, and also a near memory accelerator for fast retrieval. And the query here is compared against a subset of quantized database vectors, and then the nearest neighbors of this partition are then sent back to the CPU server. So the CPU server will aggregate the results from all the retrieval accelerator and forward the retrieved knowledge to the GPUs. So the LLM can finally integrate the retrieved knowledge into the generation process, and that wraps up the overall procedure of RAG serving on Chameleon. Now we have a general understanding of the system. Let's delve into the details about how we design the retrieval accelerator itself. So from the accelerator perspective, one of the key components is the near-memory proto-quantization decoding unit. It loads the quantized database vectors from the memory and compare them with the query vectors. And these fast specialized units make the search much more efficient than CPUs. And compared to GPUs, Chameleon uses the cheaper DDR memory in order to hold a large amount of vectors. And besides, unlike the throughput-oriented GPU designs, Chameleon can simultaneously achieve low latency and high throughput because it uses all the processing elements to process a single query. Now let's first take a look at the decoding unit. Here, the decoding process involves many lookup operations. It first fetches the PQ codes from memory, and here the decoding process basically uses each byte of this PQ code as an address to fetch another value in the distance lookup table. And this very intense fetch operations essentially becomes the bottleneck if we do this process in CPU. So to address this, Chameleon instantiates many of these parallel on-chip SRAM slices, and they hold different columns of these distance lookup tables. So we can load an entire database vector from the memory and finish all these fetch operations in parallel just within a single clock cycle. And then these retrieved partial distances are summed up by an adder tree, which produces a result distance between a query and a database vector. Also, all these input, lookups, reduction sum, result ejections are pipelined, so a decoding unit can achieve a very high throughput of producing one result distance every single clock cycle. Since we have dozens of these very fast BQ decoding units, there are also dozens of result distances being produced every single clock cycle. So the next question here is that how can we collect the k-nearest neighbors rapidly so we match the pace of these decoding units? For this, we use a hardware primitive known as systolic priority queue. Essentially, a systolic priority queue is a register array that is connected by compare swap units. I'm going to skip its technical details, but at a high level, it has a very high ingestion throughput, can ingest one input value every 2 clock cycles. So as a result, each PQ decoding unit is followed by 2 of these queues because each PQ decoding unit outputs one result every single clock cycle. On the other hand, the hardware resource consumption of these queues is also pretty high. For each of these queues, both of the number of registers and compare swap units are linear to this queue length, which is equal to the number of nearest neighbors we want to return. And then we'll need dozens of these queues on the accelerators, and actually twice as much as those PQ decoding units. And this leads to a critical problem because given this many of queues, even if we instantiate this accelerator on data center class IPJs, we still don't have enough resources to instantiate these units due to the high hardware resource consumption. So the question here is that how can we still achieve the same high throughput but significantly reduce the hardware resource consumption? And before illustrating our solution, let's first analyze an example. Let's say we want to use 16 of queues here to gather the top 100 nearest neighbors. And one question we ask here is that, is it really likely that all 100 results happen to be located in one of those queues? As our mathematical analysis confirms, it's actually highly unlikely. As you can see in this plot, the x-axis represents the number of neighbors that a queue contains, and the y-axis shows the probability distribution. And from this plot, we can find that it's extremely unlikely that a queue will contain more than 20 out of the 100 nearest neighbors. So based on this insight, we propose the approximate hierarchical queue architecture. And the key idea here is that we can significantly truncate the length of these queues while still achieving similar K selection quality. For example, we can set a quality requirement of achieving identical results in 99% of queries. And with such a quality requirement, we can then explore the degree of truncation we can do. And the more queues we have, the less likely that one queue will contain many nearest neighbors. And as a result, we can reduce this length of these queues by up to 10 times given 32 queues without notable recall degrade. So in summary, the retrieval accelerator in Chameleon have very fast PQ decoding units as well as high throughput while resource efficient top K result collection units. Now let's take a look at its performance based on our FPGA prototype. So the violin plot here shows the vector search latency distribution of Chameleon and the baseline systems in log scale. And specifically, Chameleon used GPUs for index scan and also FPGA prototype retrieval accelerators for scanning the database vectors. And for baselines, it can either be pure CPU-based or hybrid CPU-GPU baseline, where the small index is scanned on the GPU. Here, Chameleon shows up to 16 times of speedup compared to the CPU and hybrid CPU-GPU baselines. And apart from the pure performance, we also measure the energy efficiency in terms of joule per query. And across different settings, Chameleon achieves up to 26 times of improvement compared to the CPU baselines. And finally, by having the accelerated vector search system in the end-to-end RAG serving pipeline, Chameleon achieved up to 2 times of speedup in terms of latency and 3 times of improvement in terms of throughput. So in summary, RAGO and Chameleon represents two early efforts in addressing RAG serving performance at the system level and at the hardware level, respectively. Apart from RAG and vector search, I also work on recommender systems, data systems on modern hardware, etc. And from all these projects, you can find that many interesting research actually happens across computing stack. In the future, I believe this cross-stack optimization will continue to play a key theme in designing the next generation of machine learning systems. We'll need to optimize algorithms, optimizing data systems, design better system software, and also building customized hardware. With this, I conclude my talk here, and please let me know if you have any questions.